Yes, sir.
Okay, good. So let's begin. So today basically we'll be talking about just a brief description on deep learning and specifically on convolutional neural network. Okay, so let's begin. Okay, so we start with the introduction. The basic question is all about computer vision. Okay, so we already know that classification can be applied to different domains. It can start from economics, it can start from medical image processing, okay, from social science. Different areas are there. So nowadays, what we see that these deep learning approaches, okay, they have become popular in computer vision problems. So, can anyone of you can tell me which areas are falling under the domain of computer vision, and why is it called computer vision? Anyone? Okay, how about human beings? So basically, we use our eyes to see something, right? Whatever is happening around us, and then that is our vision system, right? We see with our eyes, we capture the picture in front of us, and we know that a sequence of pictures basically is going to produce a video in case of computers. And from those images, what we do, we try to recognize or we try to take some decisions. Okay. The same thing is applied for computers. So for the computers, we have built the eyes for it. What eyes have we built for the machines? We have built the cameras, right? Can you hear me? Okay.
Yes.
Let's say if we have a common example here, let's say the first one, image classification. Okay, that means if we have a picture of this object. Okay, now we know that exactly this object is cat. Okay, so if we want to do this classification, whether it's a cat or not. Okay, so it's a basic classification problem, and the input data we are working with is basically it's an image. Okay, the same thing if we extend it to object detection. Okay, not only we want to decide whether it's a cat or dog or whatever. We can see that in this image there are multiple objects. Okay, so let's say here we are focused on whether we can take these three objects, whether there is a dog, whether there is a bicycle, or whether there is a truck. Okay, that means we are doing object detection. If our capacity of this machine learning approach increases, we can even detect maybe the pillar is there, the road is there, behind the scene, the trees are there. Okay. So other interesting applications also exist in computer vision. For example, neural style transfer. Time to time we see that in the Facebook or in mobile apps. Okay, these kind of applications become very much popular, right? For example, what it does in case of neural style transfer, since we're using a neural network, so it's called neural style transfer. So the style transfer is the main thing. So here what we can see, the reference image over here, okay, the reference image you see over here is basically the style image. And let's say here we have a painting of a famous Russian painter. Okay, and then on the left hand side, we have this content image. Okay, the content image, what we have basically just a picture of a dog. Okay, a plain picture. So if we can borrow the style of the reference image and take the content from the content image, and if we can combine this together, then the resultant image will be something like this. So this is basically what we have is the output. That means we simply have transferred the style of what the reference image to the content image, right? I believe some of you have used this kind of application in the computer or in the mobile phone. Yes or no?
Yes.
So these are basically computer vision problems. That means the main thing is that the input is going to be image, or maybe it's going to be the videos. Okay, this is what we have, and then we are going to take some classification or detection problems or image generation problem. Okay, so all those things will basically falls under the domain of computer vision. Okay, since we are learning about machine learning, so we will try to see how does machine learn those things and give us the output that we are expecting. Okay, okay. Now, why deep learning? Okay, that is why are we using deep neural network? Okay, the reason is that if we look at this image, okay, let's start with the basic image. If the size of the image is 64 by 64, and I believe you have the idea that an image, how many color channels do we have in an image?
3 normally.
3, yes. That means basically we know that each of these colors, whatever the colors we can see, we have a red channel, we have a green channel, and then we have a blue channel, right? That means if the image is basically 64 by 64, what will happen? Another plane will be there. First one will be red, the next one will be for green, and the next one will be for blue. So if we combine all this information together, basically we have this color image. So this is basically, if you think about a grayscale image, okay, in case of a grayscale image, what we have? Okay, in case of grayscale image, basically we simply have one plane. We don't have multiple planes. So this could be, in this case, it could be 64 to 3, and here it will be 64 to 64 into 1 if I write like this. Okay. So we don't normally write multiply by 1, just simply write like this. Okay. So if we look at this image, okay, so if I say that if I convert this whole image into a vector, okay, the whole image in a vector, so how many input values do we need to deal with? What do you think? So you can see that this many input values you are going to have, okay? If this image, because we know that 64 to 64 is quite a small image, right? It's a very small image. Normally you take pictures with megapixels, right? Yes or no? So even if we take a comparatively a little bit larger image, the size of 1000 to 1000, and it has 3 channels, basically we will have 3 billion color values. And since we have 3 billion color values, now the question is that if I want to design a neural network, okay, so like the one that you can see on the right, bottom right of this image. So as we have said that if I convert this image, okay, if I convert this image to a 1D input vector, then how many input values are you going to have? We're going to have 3 million input values, right? Yes or no? Okay, fine. And we know that in the input layer of our neural network, we have to have that many nodes for the input. So since we have 3 million input values, so basically the value of n is going to be what? It's going to be 3 million. Let's say if I simply take a small network, I'm not defining a large network. Let's say if I define a small network like this, where basically I have 2 hidden layers, and then maybe I will have one output layer to decide whether it's a cat or not. So if it's cat is 1, if it is not cat, so it's going to be 0. But you can see that in the first hidden layer, if I only give 1000 hidden nodes in the first layer of the hidden layer, so basically only in this first weight vector, if you just simply even forget about this bias, in the first one, let's see if I say W1, in W1, how many parameters do you have to deal with? So first of all, what will be the dimension of the W1 matrix, the weight matrix? What will be the dimension? Yeah, 1000 into 3 million. So that means basically only in the first layer you have to work with 3 billion weights. So basically it's too much, right? Yes or no? And then you have to also consider the other layers. Whatever the other layers you are defining over here, if you increase the number of layers more and more, higher and higher, what will happen? These values will be very large, right? Yes or no? So basically, in this case, you can see that a conventional design of a neural network, you have to deal with so many parameters. And since we were going to use an optimization algorithm to learn those parameters, it's going to be very time consuming to learn all those parameters. Okay. So this is actually what we're going to do. This is why. So this is why. Here, what we'll have in case of this deep learning approach, we'll see the concept of convolution. Okay. The concept of convolution, that means if we include convolution layers, it can provide a solution to this particular problem. Okay. So from here, what have we learned? We have learned that basically with computer vision problems, since the input is images or videos, the number of input is too many. And if the number of input is too many, if we define a conventional neural network, even if we define this deep neural network with a lot of layers, even the first layer, okay, the first layer, we have to deal with billions of parameters. And if we have defined a deep neural network, you may have to even work with even several multifold of that number of weights. Okay. So this is actually what we will do now. To get rid of that kind of problem, we will use this concept of convolution, and we'll define convolution layers and see whether it helps us or not. Okay. To start with this one, so why are we going for convolution neural network? It is in short known as CNN or ConvNet. Okay, why are we going to do that? So in the previous lecture, I have ended up with this particular figure. Okay, this first figure that you can see over here. What we have mentioned here that as we go through the different layers, what do we want to do? We want to extract. We start with low-level features. We then go for intermediate features, let's say mid-level features, and then maybe combine the mid-level features, we can go even to higher-level features, so something like this. So basically, at the end, what we can have, we can do maybe some face recognition problem we can build up. Is this understood? So basically, what happens, since in the very beginning we have the input of a face, I have a face over there, and some people's faces there. Okay, so what we do in order to extract features, because we know that as we move forward toward higher level layers, we extract higher level features. That means here what is important, that means we are doing this feature extraction. Okay? To start with the basic feature extraction method, which is known as the edge detection problem. Okay, so edge detection is basically done with the help of convolution of a filter. Okay, I will talk about filter later. Okay, so that means basically what we do this convolution operation with a filter. Okay? Let me write over here with a filter. So this is I'm talking purely from the point of this process. Okay? So the thing is that once we have a filter, okay, this is going to detect an edge. So this edge will give us either vertical edge, or it will give us horizontal edge, it will give us diagonal edges. Can you see the figure? Can you see that vertical horizontal edges? Yes or no? Okay, since we can see those edges, that means basically what we have found from this. Let's say if I want to detect this, let's say I want to detect this human being over here. So before detecting this human being, what I have to do, I have to detect the edges first. Okay, I have to pick a different color maybe. I have to detect the edges over there, maybe the edges over there, and then once I can detect the edges, then going forward with high-level features, maybe I can detect the human being. Even though I cannot see the details of human being, but simply from the silhouette of the human being, I can say that okay, that's the human being. Even maybe I can say that okay, there I have a bird, okay, and so on. Okay. So basically, the question is that what is a filter? As we have found two new terms here. What is a filter, and what is this convolution operation? Okay, and then we'll see. Okay, how can it detect the edges? Okay? So to start with the definition, okay, this is what we have. The convolution operation. Okay, so we know that an image is nothing but a collection of intensity values or color values. Okay, so think from the basic point of view. Okay, let's say we have a 2D array. The array size is 6 into 6, and then we have filter. Okay, the filter is again in this case we have a 2D filter, and this filter you can see that the filter contains some values. Okay, so these are called the weight values or the filter values. Okay, now you can see that. What is the size of this filter? Can someone tell me?
3 by 3.
Into 3.
Okay, yeah, 3 by 3. So what we will do, let's say I'm going to overlay for the very first step. What I'm going to do, I'm going to overlay this filter on the input image. Okay, if I overlay the filter on this input image, so you can see that this filter will be placed exactly here, right? Yes or no? Right?
Yes, sir.
Okay, so then you can see that first, in this case, you have to define the center of the filter. So the center of the filter is basically this one. So if I look at the center of the filter, I have placed the center of the filter exactly where? Exactly over here. Now, once I have overlaid the filter over there, I can easily see that which value is going to be overlapped by which value. So 4 is going to be overlapped by the filter value of 1. 9 is going to overlap the filter value of 0. Then -2, -1. then we have 1, 0, then -1, then 1, 0, -1. You can see that how they're going to be overlaid with each other? Yes or no? But this overlay means basically what we are doing element-wise multiplication, and the convolution operation says that do this element-wise multiplication and sum it up. So if I do this element-wise multiplication, you can see from here 4 times 1, what do we have? 4. 9 times 0, what do we have? It's 9. So all these positions, what we have done this element-wise multiplication, and if you sum it up, what is the summation value? What is the sum value?
2 here.
It is 2 here, right? And this is basically your convolutional response for this particular filter at this particular position. Is this understood?
Yes, sir.
Is this understood for the other people?
Yes, sir.
Okay.
Yes.
So next what we're going to do, so this is step 1. And now what we'll do in step 2, we'll simply move this. Okay. So previously, where was our filter? Our filter was here, right? Right? And what we have done, we have simply moved the filter, okay, one position to the right. That means previously it was here. Now we have placed where? Now we have placed it here. If I place it here, now you can see that the same filter values is going to be overlaid with a different set of values. Correct? Yes or no?
Yes, sir.
And if they're overlaid with a different set of values now, so if I look over here, what values do we have here? Similar as before. 1, 0, we have -1, we have 1, 0, -1, we have 1, 0, we have -1. And then if we do this element-wise multiplication, that means 9 times 1, 2 times 0, 5 times -1, and so on. If we do this element-wise multiplication, add them up, and the convolution response for that position, what we have? For that position, we have a value of what? Value of 6. So in this way, then the next what will I do? I will shift it 1 pixel to the right. Correct? Okay, so if I do that, so what will happen? I can go over here. Okay, fine. And then if the next step, what will I do? I will move 1 position even to the right, and I will come over here. Is this understood? Once you have reached this position, then what do we do? Then we'll move 1 pixel down. That means we'll move from left to right, top to bottom, and you will end where? You are going to end whenever you are going to reach to this particular position. Is this understood?
Yes, sir.
So basically, you can see that I have visited this one. If I consider the center pixel has visited this position, that one, that one, that one. This one, and that one, that one, that one, that one, and that. These are the positions where you have placed this filter. Now, how many positions have you visited?
4 into 4.
We have visited 4 into 4 places. That means we have visited 16 places. And then if you visit all those positions, do this convolution operation and store the result, you will find all the values over here. So is the convolution operation clear? Yes or no?
Sir.
That means basically we will have a filter. And the filter value, not necessarily the filter value have to have, the filter values will have to have these values, okay? These can be any values. Whatever the values you will define, accordingly you will get the filter response that we have seen over here. Okay? That means if you change the filter value to something else, do you think you will get the same value of 6? No. You may get a different kind of values. Okay? Now you can see that previously the input array or the input matrix had a size of 6 into 6, but with the filters of 3 into 3, the output now have a size of what? What size do we have seen? We have seen we have a size of 4 into 4. That means somehow you have seen that convolution operation in this particular case have shrunk the matrix size. Can I say like that?
Yes, sir, we can.
Okay. Now the question is that why do we need to do this convolution operation? So you can see from here Can you see the animation? How the convolution is going on one after another? So this will happen for even a bigger image, okay, or a bigger matrix size. Okay. The question is that why are we going to do this convolution operation? Okay, that means we want to define a convolution layer. So we understand what is the convolution operation, but why are we going to do it in case of our deep neural network, okay, or even neural network architecture? Why are we going to do it? First of all, you can see that this gives us two benefits. First of all, it will give us the benefit of parameter sharing. What does this mean? Because you can see that if the parameter values, like if I define over here 1, 0, let's say 0, -1. If I define the filter values like this, you can see that for different positions, we are using the same set of parameters, right? Yes or no? Correct? Oh, sorry, I just put my mistake. The filter should be just over there, right? Let's see if I put this filter value, what should I put it? Let's say 1, 0, -1. 1, 0, -1, then 1, 0, -1, okay? So you can see that the same set of filter values are going to be used. So that means basically what we are doing, we're doing this parameter sharing, right? Yes or no?
Yes, sir.
Okay. And then what we see, another benefit we have is the sparsity of correction. The sparsity of correction means if you look at the output value, this output value only depends on a small portion of your image. And the second output, if I look at the second output, let's say if I look at this particular, if I let me pick another color, let's say if I, where is it? If I pick this particular output value, this particular output value depends on this portion of your input. So this is known as basically the sparsity of correction. That means each output only depends on a small portion of your image. So like we have seen before, in this case, if I want to define a single filter, then how many weights do you need to learn if I don't give you the weight values like you have seen before? So these are the weights, right? So if I know this weight value, say this is your W now, if I don't know the value of this W, then for this particular problem, how many weight values do you need to know?
9.
You have to know actually 9 values. But if I didn't use the concept of convolutional neural network, then let's say for the very first layer, if your input size is, we know that we have a 6 by 6 input matrix. So basically in the input layer, how many nodes you'll have? You will have to have 36 nodes. Let's say in your first layer, you have 100 nodes, the hidden layer. Then the weight matrix, W1. What will be the size of this matrix, W1? It will be 100 into 36. That means even for that layer, you have to learn 3600 weights. So that means instead of learning 3600 weights, how many weights do we have to learn for this particular example?
9.
So do you see the benefit of it? Now, the question is that whether it will work or not. Okay, so that's very important. So that's what we're going to see now. So let's see the example of vertical edge detection. Now the question is that why will it work? Okay, so already you have got the idea. That means basically this filter, whatever the filter size, let's say I have designed this filter. Okay, I'm just showing it again: 1, 0, -1, 1, 0, -1, 1, 0, -1. So now we know the concept of convolution. Now whether we want to see this filter, okay, the filter that we have just drawn over here is going to detect vertical edge or not. Okay, and from the point of convolution, what do we do? Like I have said, this filter will be overlaid on the pixel positions, okay, or the matrix positions, and then you will place it, and then you compute the values. You place it, compute. Let's see if I place it here. The first position, I will get this value. The next, I placed it here, I will get this value. Then the next I place there on this position of 9. If I center over there, I will get this value. Finally, on this position, I reach here, I will get this value. Once I have reached the end of the edge, I will go one step down and I will repeat the same thing again and again. In this way, you can see that you will get these particular responses. Okay, so these responses for the time being, it is not kind of meaningful to you, is it? Yes or no? No. So let's look at a much simpler example. Okay, simpler example. Okay, let's move to. But is the concept of convolution clear? Yes or no? And this star, okay, this star symbol basically is going to represent the convolution operation. Okay, sometimes you'll also see a star like this. Okay. You'll also see a star like that one. Okay, let me ask someone. Let me see. I'm going to ask questions now. Okay, let me see. Bhuyan Sanjit Shofik. Can you hear me?
Yes, sir.
Okay. Can you tell me how did we get this value of -3 over here?
So this is basically the second last operation of the
Okay,
convolution.
second last. So basically, tell me, where did you place this center of this filter?
Sir, at
Tell
6.
me which at 6, right?
Yes,
Okay,
sir.
if you place it here, then the whole filter will go where? The whole filter will come somewhere
Yes, sir.
there, right?
317. Yes, sir.
Okay, and then which value was multiplied with which one?
So the 10 minus 1 will be with 317 and respectively.
Oh, okay. That means this you will have 10 minus 1, 10 minus 1, 10 minus 1. So you will do the elementary multiplication and sum them up, right?
Yes, sir.
Okay, good. Thank you. So this is the case where we'll see whether we can detect some edges. So edges means what? That means there is a change in the color value, right? So let's say in this side you have some values. The values are, let's say, something like 10. And on the other side you have some values of, let's say, something like zeros. So purely from the point of image, if I look at the image, so higher value means brighter the value, lower the value means, in this particular case, the darker the intensity value. Okay. So do we have an edge in this image if we consider it as an image? Do we have an edge? Okay,
Yes.
how do we define an edge? In which portion do we consider that to human eyes we see an edge?
The intensity value changes.
Exactly. Okay, that means there's going to be a sudden change, a significant change from one level to another. If the values were something like this, on this side you had the values of, let's say, 4, on this side you have values of 3, that we have some change, right? 4 changed to 3, but the change is very small. But if the value is changing from 10, suddenly it jumped, I mean not jumped, it just dropped to 0. So what will happen? To human eye, we will see that, okay, there is a change. But basically, where do we have the edge? In the image, you see that the edge is exactly where? Over there, right? Yes or no?
Yes, sir.
Okay. So now, how does it work actually? Okay, so you can see that whenever we do this convolution operation on this image, so the image size is here, what we see. It is 6 by 6, and then with the filter size of 3 by 3, it has reduced to 4 by 4. Okay, it doesn't matter. Okay, once we have done this convolution, whenever I place the filter over here, what response did I get? I got 0, right? Yes or no?
Yes, sir.
So as if basically we are simply, if I consider that this position, okay, this position defines the edge location. So basically we are taking the difference between the right hand side with what? Left hand side, right? So now if the zeros will be multiplied with these 10s, so forget about those. Now on the right hand side, these minus 10s are being, I mean these 10s are being subtracted from which one? Of the left hand 10s, right? Yes or no?
Yes, sir.
That means we have minus 30 and here we have plus 30, and if we add them up all together, what will we have? We have the value of 0, right? Yes or no?
Yes,
So
sir.
basically, purely from the point of first order derivative, you know about the first order derivative, right? Rate of change? Yes or no?
Yes, sir.
Yes, sir.
So if we have a fixed area, let's say all the values are same, let's say we have values of a, then at this position, let's say at this position, the first order derivative value is going to be the next value minus the previous. What's the next value? The next value is a. What's the current value? The current value is a. So basically, the first order derivative will give you, say, the value. This is the value of f. First order derivative will give you exactly for this position. It will give you a derivative value of what? It will give you a derivative value of 0. Yes or no? Okay. How about if this value was, instead of being a, then next it was 0, 0. This is what we have in the image. Okay. Now, if this was the input value, then exactly for this position, if I compute the first order derivative, what will be the first order derivative value?
Minus A.
This will be minus a, right? Or if you consider the other way around, let's say it was 0, 0, just to make it simple. At this position, what will be the derivative value? The derivative value will be a, right?
Yes, sir.
That means basically, whenever there was a rate of change, if you consider purely from here, whenever there is a rate of change, you have a non-zero derivative there, right? But if the values were fixed, let's say a, and so on, then the rate of change will be what? There is no change, so of course the rate of change will be 0. So basically what we have got here, we have got a filter that's tried to approximate the first order derivative. That means the previous value minus the next value. Okay. So if this is the case, do we have a flat area over here? Fixed area over here? Yes or no? Do we have a fixed area? Okay, so then what will be the derivative value? What will be the derivative value? It's going to be 0, right? Right? Okay, now let's move one position to the right. Let's see what happens. That means if I place my filter here, okay, I'm just showing you the center. Okay, first I'm showing you the center of the filter, and my whole filter will be something like what? It will be something placed over there, and then you know that where is going to be your filter width. So it's going to be 1, 0, minus 1, 1, 0, minus 1, 1, 0, minus 1. So you don't have to worry about the zeros in the middle. So on the right hand side, what values do you have? So 0 times minus 1, so it's going to be all zeros. And the left hand side, what values do you have? You have 10 plus 10 plus 10, so it's going to be 30. So 30 minus 0, what value do you have? The convolution value? You have 30, right?
30, yes, sir.
That's a non-zero value, yes or no? It's a non-zero value. Now, if I purely see from the point of the concept of derivatives, so in this position, is it a flat area? Is it a constant area? Is it a constant area?
No,
Yes
sir.
or no? No. Because at some position we have some 10 values, on other positions we have 0 values. It's not a flat area. So you can see that that's why you have a non-zero value. Even if I want to move my filter one position to the right, okay. So if I'm here, again my filter will be where? This is where my filter will be placed at. So again, do I have a constant area? Yes or no? No. Again, what do we see? For that position, I have a non-zero value. But next, if we move one position to the right again, okay, that means once I have reached here, that means I have placed my filter over there. Now, do I have a flat area, constant area?
Yes, sir.
Yes. So that's why you can see that we have the value of 0. Now, once you have done this convolution operation for the whole image, this is the output that you get. And then you can see there that those non-zero values, somehow, did they identify the edge region? Yes or no? So basically, which positions have you visited? Basically, you have visited all these positions, right? Yes or no? Okay, fine. So in this position, where was the edge exactly? The position was in between 10 and 0. This is where you had the edge, right? Okay. And then if you see that those edge positions have been identified by both sides by these values of 30. That means this 30 shows you the one side of the edge to the right, another side of the edge to the left. Is this understood? Yes or no? Okay. First of all, this was your input matrix 6 by 6. Which positions have you visited? These are the positions that you have visited, right? That's why, I mean, since you have posited these 16 positions, that's why you have produced an output of how many values? 16 values. This 4 by 4 output values you have, right? Now, if you only concentrate that portion of your matrix, where was the edge? Okay, in between 10. But basically, can you locate the in between positions between 10 and 0? Can you locate that one? Exactly, in terms of index? Yes or no? We are saying in between. But if I were to say, okay, where was the edge? How will you locate? You can either say here was the edge, or you have to say there was the edge. Yes or no? Right? So the thing is that if I consider both of them as the location of the edge, did the output of the filter give me those location, edge location? You see, that means, I mean, for this position, what is output value? 30. For this, all these positions, this is the basically where you have got the response of what? All these filter response of non-zero 30. Yes or no? Then where was the edge? In between those two positions, right? But normally we don't say in between, can we? Because these are the index. What is the index position? The index position goes for this is the center of the cell, right? So can you give an index position for in between two cells? Yes or no? No. So that's why what do? We say as a whole together, this is where we have my edge in the image. Understood? That means the non-zero values will give you the location of the edge. Understood? Okay. So now basically that is what I have said. Since it computes difference between the, let's say, right hand side with respect to the left hand side, what kind of edge have we detected?
Vertical edges.
Vertical edges. So if I ask you, if I want to detect horizontal edges, so what filter should I have designed?
Transpose this filter.
Yeah, let's say I have to do yes, horizontal, okay, horizontal. So basically what I have to do, so since my edge, let me draw like this, my edge should be horizontal like this. The filter values I should have picked should have been something like what? Let's say 1, 1, 1. Over here it should be 0, and then here it should be -1, -1, -1, right? So if I have an filter like this one, this filter can detect which kind of edge?
Horizontal edges.
Horizontal edges. And now if I ask you if I were to have, I mean, diagonal edges, what will happen?
So then we'll have zeros across the diagonal and then one elsewhere.
Yes. So that means basically, if I simply give you a hint, simply look at the position of the zeros can give me the alignment of the edge. Yes or no?
Yes, sir.
Yes, sir.
Yes, sir.
Very good. Okay, so we are not going to basically focus on edge detection. In case of filters, we'll learn more in image processing course in the next semester. The thing is that what we have seen that by changing the filters, okay, this is very important. Now we want to move towards the convolution concept by changing the weight value. So what we see over here, whatever we see here, we can detect different kind of features. Let's say for this filter, this is what will give us horizontal edge features, right? Sorry, vertical edge features. Yes or no? This one.
Yes, sir.
This is the first one, and this is the second one. If I change the filter weights, it gives us what kind of filter? A different kind of filter feature, or if I simply say it will give us the horizontal edge feature. So that means what we have learned, if we can define the weights of the filter in a right way, we can correct a good feature. Can I say like this? Okay. Okay, that will come to later. Let's say if I gave you the filter weights, will you be able to extract features? Okay,
Yes,
and then what we have started from the very beginning. That means in case of this particular example, okay, in this particular example, what we say, if we can define a neural network, which will start with extracting low-level features, and one of the low-level features, what we ask for, we ask for edge features, yes or no? Then in order to detect the edge features, then what will we need? Let's say if I want to detect horizontal edges, I have to have some filter which will detect horizontal features. If I want to detect vertical features, I have to have another set of features for vertical features, vertical edges. If I want to detect diagonal edges, I will have to have another filter for diagonal, yes or no? So do I have a single filter or I will have multiple filters?
Multiple filters.
Okay, that's what we have here. That means in this example, if we start with two filters only, one let's say horizontal, another filter for vertical, then these two filters can give us two different set of edge features, right? Yes or no?
Yes,
Now,
sir.
once I have got these edge features, from these features, if I can again extract some high-level features, that means if I can extract some mid-level features, what can I extract? Maybe I can extract some human body figures, yes or no? If you can extract even higher features, what will happen? We can even detect the human being, yes or no? So do you get the understanding that how filter and convolution is going to help us?
Yes, sir.
Okay. Now we know that why we need to have this convolution operation, and during this convolution operation we have to have a filter, right? So no. Now the question will come next. Where is okay? The question, as you can say, okay, let me just finish with this one. So as I'm telling you, that basically we want to detect edges. If that's the goal, there are different kind of filters. The one that we have already seen is the basic one, which is basically trying to approximate the gradient filter or the first order derivative filter. Okay, and the same kind of approximation can be done with other popular filters. Let's say this filter is known as the Sobel filter, also for edge detection. There is another filter which is known as the scar filter. Same thing, it will detect edges. Can someone tell me, Sobel filter that I can see here, which edge will it detect? Horizontal or vertical?
Vertical edge.
Vertical. How about the scar filter? Vertical. So what is the difference? You can see that the weights are a little bit different, right? Yes or no? But still you can see that the basic approach you see is that it is simply taking the difference between left hand side and right hand side, right? Okay. So that means basically if we can detect the weights good enough, then basically we can detect some good features. Now the question is that which features are important? If I ask you, what will be the answer? Listen, purely from the point of this. Now let's say I haven't defined the weights. I'm simply writing W1, W2, W9 for this 3x3 filter. Let's say I want to extract a good feature. Okay, this is the output. Output is basically what I have extracted as features. And this convolution, the star, will help us to extract the features from the input. Okay, this is what we're going to have. The question is that which features is going to be good? Who will define that? Everything from the point of neural network. Who will define that? Let's say, sorry, cost function, exactly. So basically, we know that we are going to have our predicted outcome y hat. We're going to have our actual output of y. And if I define my loss function or cost function, the thing is that if these weights are not good. Let's say if you randomly set this weight, the values you're going to get, do you think by randomly initializing the weights, I will get good features for your desired application? Yes or no?
No, sir.
No. So that means, since the weights, as you have seen in case of neural network, since the weight was not good enough, so that's why the output, you can also say it was not good. Okay. I mean, you didn't have a good feature. You did not have. Okay. You did not have a good feature. So that's why your predicted outcome was different from your actual outcome. So now, what is your problem now?
Sir, how do we know the actual outcome?
Which one? I mean, during the training phase, of course, you are doing supervised learning. Don't you know the actual outcome?
So we are giving a picture and we are trying to get some features, but we have
Okay, this is not output actually. From these features, you have to take a decision, right? And then predict y hat, yes or no.
yes, sir.
So this is, I'm saying, in between. This is one of the point where this is one of the step where you have extracted. Let's say I have extracted some features. Let me say like this: I've extracted some features, and based on these features, you will basically predict the outcome of y hat. Okay.
Yes, sir.
Now the thing is that if your features are not right, if these are not right, okay, this is not right. So do you think from these wrong features, the prediction, is it going to be correct or incorrect?
Incorrect.
If it is incorrect, then you automatically you can identify from where? You can identify from the loss function.
Yes, sir.
Okay. And since your loss function penalty was high, what do you know? From here, what did you know? You knew that the weights was wrong. Yes or no?
Yes, sir.
If the weights are correct, let's say you have got the correct set of weights, you have found it, okay? You have found it. If I found the correct set of weights, the features I will extract will be the right features that I want, yes or no? And if I get the right features, from there, whatever the prediction you will do, the y hat you will do, the y hat prediction will be close to your actual one, yes or no?
Yes, sir.
Yes, sir.
That's why in neural network, I mean in convolutional neural network, you can see that yes, we have done this convolution operation, but the problem at hand is how do we find the weights of the feature. That means during this learning phase, during this, let's say in case of optimization, the backpropagation algorithm, what we'll try to do, we'll try to find the weights of these features. Is the problem clear?
Yes, sir.
Okay, so we'll come to that point later. So far, we just have learned about how to do correlation, how the weights are basically influencing your output. Also, we have seen that the weight definitions, that is the weight coefficients, however you define it, they will basically give you some meaningful features, yes or no? But in case of our classification problem, but in case of our learning problem, we have seen that since the features are heavily dependent on the weights of the filter, in order to get the correct set of features, we have to select the right weights for those features. Clear? Yes or no? No. You are saying that the size of the filter is 3 by 3, right? This is your input. The input is here is 6 by 6. As I said, the input is 6 by 6. Your filter size is 3 by 3. But the filter size can be anything. We'll talk about, different size filters. Don't worry. Okay. Now the next part of this lecture is basically on padding. What does padding mean? As you have seen in the previous example. Okay. In the previous example, now without the zeros. If you look at the center position, okay, the center main input matrix. What was the size of the matrix?
6 by 6.
It was 6 by 6. And you started with which position? You started with this position, right? Yes or no?
Yes, sir.
And once you've started this one, your filter was overlaid over here. And how about the very first position, 4? Why did not we place it over there? You started from 6, but why not at the very first cell? Why did you didn't start from there?
So then a few values in the filter would not be multiplied with anything at all, because
Exactly. That means if you place your filter at 4, if you place it here, then you can say if I place my filter, then basically some portion of my filter will be basically outside the matrix or outside your image, and outside the image basically we don't know what is there, do we?
no, sir.
No. But if I could somehow, if I could have placed it over there, by assuming that whatever is outside your matrix or your image, all those are zeros. Think like this. So I mean, in this particular example, for a matrix size of 3 into 3, so if you place it on the very first cell position of your input, then you can see that your cell needed to pad how many zeros all around it?
5 zeros.
I mean, one layer of zeros all around it, right? One layer of zeros all around it, right? Yes or no?
Yes, sir.
Okay, that means we are saying that basically we have done a padding of 1. Padding of 1 means one layer of zeros have been padded all around it. You can see that extra zeros are padded all around it. Yes or no? Now, if I can pad all around it, what is the benefit of it? The benefit of it, you can start from the very first cell. Also, you can end up with the very last cell. Yes or no?
Yes, sir.
And that means you can place it over here. And if I can place over there, now that is basically how many cells have I visited? I have visited all 6 into 6 cells. Then your output will be also a 6 into 6 matrix. Is it clear? But if I didn't do this padding, if I had started one cell position inside, that means if I had started from here, let me pick another color, black, maybe black, no, not black, green. If I had picked from here, what happened? You visited this cell, this one. Could you visit 3? This one, could you visit 3? No, right? So we visited all these cell positions without padding, and your matrix reduced to what? 4 into 4. But if I pad with the cells with one extra layer of zeros outside, you can see that your output will have the same size of your input. Is it clear or not?
Yes, sir.
Okay. So that means basically what will happen? You have the same size, right? So why do we need to do padding? Because without padding, what happened? So if I write like without padding, what happened? Your input size was 6 into 6, and then you did your convolution operation over here, and your output was 4 by 4. Let's say if I do another layer of convolution, that is from here I had got 4 by 4. So if I do another convolution operation over here, this will reduce to what? What will happen? This will reduce to, sorry?
1 by 1.
4 by 4. Yeah, it will reduce to 1 by 1, right? Yes or no? No. It will reduce to, you have to grab the calculator. It will reduce to 2 by 2. Yes or no?
Yes, sir.
So that means basically, if we have more and more convolution operations, the thing is that always the size shrinks. Yes or no?
Yes, sir.
Okay. But if you don't want to have this shrinking, so then what should you do? That means you want to have a convolution operation, but still you want to have 6 by 6. You want to do a convolution operation, but still you want to have this output of 6 by 6. So if you want to have same size output, then what do you need? You need to have padding. Understood? Is this understood?
Yes, sir.
Okay. Now the question is that, let's say if my filter size was not 3 by 3, it was 5 by 5. Okay? then what should be the padding number? If the padding number is called P, what should be the padding number?
2.
It should be 2, right? Because if I place a 5 by 5 filter here, it's not 3 by 3, it's going to be what? It's going to be 5 by 5. So basically we will have to have another layer of zeros outside, right? Yes or no?
Yes, sir.
So if you want to have same size padding, normally so the padding value will be equal to n minus 1 divided by 2. Is this clear? Sorry, I should have written F here because they've used the expression F. So F is the filter size. So that means if the filter size is 3, that means for the F value of 3, you should have a padding value of what? It will be 3 minus 1 divided by 2, so it will be 1. If you have a filter size of 5, the padding value should be 5 minus 1 divided by 2, it's going to be 4 by 2, it's going to be equal to 2. Right?
আমরা কি ফিল্টার সাইজ সবসময় কি অড নেব?
Yes. In this case, I mean, you see most of the cases you will see that the filter size is going to be odd. So that the benefit of having an odd size filter is that you can define the center easily. Yes or no?
Yes, sir.
How about if if I ask you, let's say I have given you a filter size of 2 by 2. Just draw it. Let's say I gave you a filter size of 2 by 2. Which one is the center?
We cannot do
Even let's say 4 by 4. Odd size, even size filter. Which one is the center? This one, that one, or that one? Which one?
we cannot define.
Yeah, we cannot define, but what we do normally, even in some cases, you see that we can have odd size filter. We simply select one of them to be the center. Let's say I have selected this one. I've selected this one as the center. You have to select one of them, right? Yes or no?
Yes, sir.
So the common approach is that you always have odd size filter so that you can easily get the center. Because we know that this center will be placed at different positions and so on, right? So this is all about padding. So the example that we have here, that means let's say if we have the first one is called valid padding. Okay, valid padding means without padding. Okay, that means the value of P is going to be equal to 0. And same padding means the input value, if the input value is n by n, the output value will be same, n by n. Is this understood? Yes or no? That means valid convolution will be the case whenever the padding value will be equal to 0. That means you did not pad anything. And if we do some padding, as I've said over here, that means the padding value will be filter value minus 1 divided by 2. If you do padding, what will happen? If your input image was 6 by 6, your output value will be also 6 by 6, right? Yes or no? But in case of valid padding, what will happen? If your input value is 6 by 6, your output value is going to be reduced. So you can see that the equation is there. If your input size is n into n, if you have done the filtering with the size of f into f, then your without padding, that means with valid convolution, your output will have the size of n minus f plus 1 into n minus f plus 1. So you can see it for here, for the value of 6 and the filter size of 3. So 6 minus 3 plus 1, it ends up to what? It ends up to 4, right? That is, you will have it image into 4 into 4. Yes or no?
Yes, sir.
But if we do same convolution, that means if we do some padding, that means for the padding here the value of P is going to be equal to 1. So if we do the padding, the 6 by 6 image will be enlarged to what? Initially it was 6 by 6, but once we have done this padding, it will become 8 into 8, right? Yes or no? And then if you do this filtering with the 3 by 3, you will see that the output filter, the output image or the output matrix will have the size of n plus twice p minus f plus 1 into n plus twice p f minus f plus 1. So basically, you see that in case of same convolution, this is going to be also n into n. Is this understood?
Say we have another class now.
Oh, you have another class? What time is it? Okay. So is this clear? Okay, so I wanted to cover one extra thing. So this thing you're going to need. I just want to give you the name. Stride. Stride means basically the jump you're making. Okay, the jump you're making. For example, let's say here what we do. We visit this cell position, and then the next cell is going to be, you pick is which one? The one just beside it, right? Yes or no?
Yes, sir.
So basically you have made a jump. Jump means stride. You have made a stride value of equal to 1. But if you take a stride value equal to 2, it means that you made a jump. Instead of taking one step, you will take 2-step jump. That means you will move to this particular step. Is this understood? And then if
Yes,
you want to
sir.
jump again, where will you move? You will move here. And then if you want to jump again, where will you move? You will move here. Is this understood? Yes or no? Is this understood? This is a jump of 2. But if you had made a jump of 1, what would you have done? You would have started from here. You would have gone all these cell positions, right? Yes or no? But here you have made a jump of 1. A jump of 1. But if you make a jump of 2, what will happen? If you start from here, you will make, instead of going 1 jump, you will make 2 jump. So that is known as stride. Stride means just step jump. Okay. So let me stop over here. So one of the groups you will have lab today. So these things are basically will be needed. So that's why I just want to tell you those things. Okay. So let me give you the link to your attendance. Okay. Okay. Why can't I give you the link? Okay. So did you get the link?
Yes, sir.
Okay. So please give your attendance. Okay. One important announcement I just forgot to tell you. Tomorrow we won't have any class. Okay. I'm going to cancel tomorrow's class. We'll continue next week, inshallah. Thank you.
Assalamu alaikum, sir.
Walaikum assalam.